In this section, we will define the functions of each major component of a reciprocating compressor. That is, what the purpose of each component is, or what it does. By understanding what each component is supposed to do, you will be in a better position to know if it's performing its duty correctly. We will present each major component, state its function, operating limits, and what exactly to look for when operating or troubleshooting a reciprocating compressor. Now, take a look at the following horizontal, multi-stage, double-acting reciprocating compressor. The mechanical components that we will cover in this section include the crankcase, the distant piece, the crankshaft, the connecting rod, the crosshead, the piston rod, the piston rings, the piston rod packing, and the wiper packing. Notice here that compressor valves are not part of the list. Why is that? Because in a reciprocating compressor, the valves, without a doubt, have the greatest effect on the operating performance of the machine, both from an efficiency standpoint and from a mechanical reliability standpoint. And this is the reason why we have designed a separate section to cover the subject of valves in exquisite detail, both from their mechanical design and operating principles, as well as how they are used to regulate and adapt the capacity of reciprocating compressors to system demand changes. Now, before to move on to the next video and start exploring the various mechanical components, we would like to inform you that the next couple of video lectures making up this mechanical design section are not interrelated. So feel free to jump to the lectures that most interest you, especially if you're a little bit more advanced. However, if you're starting from scratch, then we strongly recommend you to start from the beginning. The first mechanical component we will cover is the compressor crankcase. The crankcase, as highlighted here, supports the crankshaft bearings, provides a sump for the bearing and crosshead lube oil, and provides support for the crosshead assembly. Typical crankcase condition monitoring and safety devices are relief device to prevent crankcase breakage in the event of explosion caused by entrance of process gas into the crankcase, breather vent to allow removal of entrained air from the lube oil level gauge to allow continuous monitoring of crankcase lube oil level, oil temperature gauge to allow continuous monitoring of lube oil temperature, vibration detector to provide information concerning crankcase vibration, which is useful in detecting dynamic changes in the running gear, low oil level switch to provide alarm signal on low crankcase oil level, and finally lube oil pump, which is shaft driven. This pump, which is a positive displacement type of pump, is directly connected to the crankshaft and discharges oil directly to crankshaft bearings, connecting rod bearing, crosshead shoes, and crosshead pin bushing via precision bore in crankshaft and connecting rod bearing. We will see this in detail in the compressor lubrication section. Now, an important reliability consideration is to make sure that the crankcase is securely mounted and level. This requires proper grounding and maintaining a crack-free base support. Since the dynamic forces on the crankcase and crosshead mounting feet can be very large, it is usually common to use an epoxy grout. Epoxy grouts provide high bond strength and are oil resistant. All reciprocating base plates should be checked on a continuous basis for any evidence of foundation cracks or discontinuities, and should be repaired at the first opportunity. The distance piece, as highlighted here, prevents contamination of process gas as well as contamination of the crankcase lubricating oil. The proper operation of the distance piece, baffles and seals, as highlighted here, is essential to maintaining reciprocating compressor safety and reliability in process gas applications. In most refinery process gas applications, a double compartment distance piece, as highlighted here, is used. This is to make sure that contamination of the crankcase or cylinders does not occur. Usually, the end of the cylinder compartment contains a partial nitrogen atmosphere, since the packing rings are usually nitrogen purged. Here, reliability considerations concerning this assembly are to make sure of the proper packing, partition packing, and wiper ring clearances. We will see this in detail further ahead using 3D animation and cross-sectional views. This figure presents a cross-sectional view of a typical double-acting compressor. Starting our way from left to right, you can see the oil wiper packing, the piston rod, the rod packing, the piston rings, and the compressor valves. The part highlighted here in yellow is the compressor cylinder. A typical reciprocating compressor cylinder consists of a barrel, usually water-jacketed, with a front and rear head. In some designs, the rear head is an integral part of the cylinder barrel. This is the case here in our example. In others, it is a separate bolted piece. These heads are also water-cooled to remove the heat of compression. Provision is made in the rear head for the pressure packing as highlighted here. Valves are installed around the barrel, but in some designs, valves are installed in the heads. Cylinders may be double-acting, as is the case here, and so compressing the gas on both sides of the piston, or single-acting and therefore compressing the gas at either the head or the crank end, but not both. Keep in mind, all cylinders can be modified to provide capacity control, or to provide openings for clearance pockets and internal plug and loaders. This will be discussed in detail in the capacity control section. By arranging the cylinders of the reciprocating compressor in various combinations, greater capacity and output can be achieved. Let's have a closer look. In this first example, single-frame, straight-line reciprocating compressors, as seen here, are horizontal or vertical double-acting compressors with one or more cylinders in line on a single frame, having one crank throw and one connecting rod and one crosshead. These compressors may be belted or motor-driven. V or Y-type reciprocating compressors are two-cylinder, vertical double-acting machines in which the compressor cylinders are arranged at some angle, using 45 degrees from the vertical, and are driven from a single crank. Semi-radial reciprocating compressors are similar to the V-type that we have seen previously, except that in addition to the double-acting compressor cylinders, arranged at an angle from the vertical, horizontal double-acting cylinders are also arranged on each side, all operated from a single crank pin. Duplex reciprocating compressors, as seen here, are machines with cylinders mounted on two parallel frames connected through a common crankshaft. Next, four cornered motor-driven reciprocating compressors are of the duplex type with one or more compressing cylinders on each end of each frame. The driving motor is mounted on the shaft between the frames. And finally, horizontal opposed reciprocating compressors, as depicted here, are multi-cylinder machines on opposite sides of the crankcase. They employ a multi-throw type of shaft with one crank throw per cylinder. In this arrangement, power is applied at the end of the shaft. Cylinders are made of material selected for the particular pressure and gas being handled. Variables which must be considered in the selection of materials include cylinder bore diameter, pressure differential, and the type of gas to be handled. For low and medium pressure cylinders, these are normally made of cast iron, but are also available in cast steel, depending on the application. In most designs, the cylinders may be furnished with liners or sleeves. These cylinders normally have generous water cooling around the bore and in both heads. Pressures can be up to 2000 psi, depending on the cylinder bore diameter. Medium to high pressure cylinders have heavier wall sections and smaller bores. The material in this case would be normally nodular iron, but steel has been used in the past. Cooling and control options are similar to those in low and medium pressure cylinders. In this arrangement, pressure ranges is from 1000 to 2500 psi, depending on the cylinder bore sizes. Finally, high-pressure cylinders are made from steel forging, with only nominal water cooling as compared to the other cylinders. Because the smallest possible number of openings in the forging is desired, capacity control mechanisms are not normally provided. Tie bolts may be installed perpendicular to the bore to pre-stress the forging, decreasing the maximum tensile stress induced by the gas pressure. Valve ports are finished to a highly polished surface, which reduces the maximum tensile stresses. In this arrangement, the pressure range for these cylinders is approximately 2000 to 8000 psi. In this video, we're going to talk about cylinder liners. Recall, this is our compressor cylinder. Let's have a closer look. The liners are located at this level, highlighted in this example in red. Liners, also called sleeves, are used in compressor cylinders either to form the cylinder wall or to be a removable part of the cylinder in case of accidental wear over a long period of service. The following figure presents a picture of typical liners that you may find in your reciprocating compressor. Notice here that I said you may find. Why is that? Because this piece is not always part of reciprocating compressors. As a general rule, liners are not used in low or medium pressure cylinders, where the gas being handled is non-corrosive. Liners are actually almost always used in medium to high pressure cylinders, where the gas being handled is corrosive. Certain industry users insist on liners in their reciprocating compressors. Liners have become standard design for certain industry applications, even though the gas involved may be non-corrosive. Such a standard exists in natural gas pipeline transmission service. The API 618 specifications for reciprocating compressors also reflect this demand. In this course, I will be referring to the API 618 standards many times, as I consider them to be the Bible of reciprocating compressors. API stands for American Petroleum Institute. Now, what I want you to keep in mind here is that using liners is a smart way to protect your compressor cylinder and reduce in a significant way your maintenance or repair cost. Because, to put it simply, a liner which increases the initial cost of the compressor cylinder is more economical to replace than the complex cylinder casting. Another application of the liner is to reduce the cylinder bore size to meet certain capacity conditions. Actually, by installing liners with different bore sizes, the same cylinder casting can be used to accommodate a range of capacity and pressure conditions. Cast iron is used for liners unless the cylinder is high pressure, above 3000 psi on lubricated machines, and above 500 psi on non-lubricated compressors. On these, hardened cast steel may be used. For corrosive applications, a cast iron which contains 20% nickel is used. The design and the materials used for reciprocating compressor pistons will vary with the make, type, and application of the compressor. Pistons are actually designed to take into account a number of conditions, such as cylinder bore diameter, discharge pressure, compressor rotative speed, compressor stroke, and piston weight, just to name a few. Compressor pistons are typically designed as one of three types. These are one-piece, two-piece, or three-piece pistons. Let's have a closer look at each type. For the first type, as the name suggests, these pistons are in the form of a single piece. A typical 3D example and its corresponding cross-sectional view are depicted here. These pistons are solid cast iron or steel for small bores and high-pressure differentials, or hollow cast iron or aluminum for large diameter and low pressures. For the two-piece pistons, these are used for bore diameters above 250 mm. Aluminum or cast iron is used, which is split for ease of hollow casting and weight control as depicted here. Notice that this type has a single rider ring carrier. This will be explained in detail further ahead. Finally, in the three-piece arrangement, the piston, as shown here, has two rider ring carriers and one piston ring carrier. Band-type riders can be directly installed into the piston grooves. Here, pistons are made of aluminum or cast iron. An exploded view of this type of pistons is depicted here. In this video, we're going to dismantle a typical three-piece piston and view its cross-section using a 3D model. Let's have a closer look. So, this is our 3D model representation of a three-piece piston. Starting our way from left to right, you can see that the piston is equipped with a rider ring carrier, a rider ring, two piston rings, a second rider ring, and a second rider ring carrier. Rider rings and piston rings will be covered in detail in a later video. Let's now dismantle the piston and observe the cross-sectional view of it. The cross-sectional view highlights the presence of an expander ring as seen here. This expander ring is located below the piston rings. Its job is to make sure that the piston rings maintain a tight contact with the cylinder internals. This will be explained in detail further ahead. Material selection for pistons is very important. Many factors must be considered. Some of these include the weight, the strength for differential pressures and inertia forces, the corrosion resistance, the compression and rider ring wall wear resistance, and the outside diameter wear resistance. In the process industry, materials commonly used for reciprocating compressor pistons are aluminum, cast iron, and steel. Aluminum is used when lightweight pistons are needed in order to balance reciprocating weights or to reduce inertia forces so they do not exceed rated frame load limits. Applications are limited to approximately 200 degrees Fahrenheit and a differential pressure of 125 psi for castings. Cast iron is perhaps the most common piston material due to its high strength and good wear and corrosion resistance. Finally, steels are used for small bore, high differential pistons when strength requirements are higher. Now, keep in mind rider bands or rider rings, as highlighted here, may or may not be used on large diameter pistons for lubricated compressors. In general, aluminum pistons do not use a rider band, while cast iron pistons will usually have a rider band. In conventional, non-lubricated compressors, rider bands are always used. In this video, we're going to talk about how the piston is secured to the piston rod. Let's have a closer look. So, recall, this is the piston, and this is the piston rod. There are actually many methods to fasten the piston to the piston rod. First, we list them, then we will see each one of them in detail. These methods include taper fit connection, interference fit connection, single knot connection, and multi-bolt connection. The depiction that you can see here shows a taper fit of the piston rod to the piston. You can think of this arrangement as if you are looking to the piston from this side here. In this arrangement, the end of the piston rod is machined to match a tapered bore in the piston. The end of the piston rod is threaded, as you can see here, and a knot draws the piston to the rod and holds it securely. A hole is drilled and tapped to accommodate a grab screw, as highlighted here, which prevents rotation of the knot and piston rod. For smaller reciprocating compressors, the interference fit is sometimes used. In this arrangement, the piston bore is machined to accept the piston rod with an interference. The piston is pinned at the rod end, as you can see here, and there is no threaded connection or knot which holds the piston to the rod. In this type of connection, the piston is held to the rod by a knot. The knot, as you can see here, is torqued depending on the material, diameter, and number of threads. The piston closely fits to the piston rod and is held on a shoulder which is machined on the piston rod. Let's now dismantle this assembly. First, the knot is unscrewed in the clockwise direction. Then the piston is slided and removed. The assembly can be made by following the reverse steps. Finally, for the last connection method, here the piston rod is flanged at the piston end, which is drilled and tapped to accept studs. The piston is also drilled to accept the studs, which are locked to the rod with nuts. Let's now dismantle this assembly. First, the two nuts are unscrewed in the clockwise direction. Then the two studs are unscrewed and removed. Once this is done, the head and piece and the centerpiece of the piston can be disassembled and removed as depicted here. The piston rod of a reciprocating compressor is designed for specific requirements of operating pressure, capacity, rotating speed, and gas composition. The various configurations which depends on piston design are single piston rod, tandem piston rod for truncated cylinder, tail rod, and cooled piston rod. For the first configuration, this type of piston rods has a single piston, as depicted in this example. In the tandem piston rod arrangement, two or more identical pistons are mounted in tandem. This type accommodates the truncated cylinder design. Here, the bore sizes at the head and crank end of the cylinder vary, and two stages of compression, each single acting, can be handled. The void space between the two pistons is connected to a low stage section, which acts to minimize the differential pressure across the piston rings. In the tail rod arrangement, the piston is in the center of the rod, as depicted in this example. The rod is of the same diameter on both sides of the piston. In this way, non-reversal loading due to equal areas and pressures on both sides of the piston is avoided. Finally, in the last arrangement, the rods are drilled through the center axis, which allows for pressure-fed coolant to be circulated through the core. Compression heat dissipation is therefore facilitated.